All right, next we have Peter Mancini. Don't forget to take your badge off. He is an RSM, a research staff member here at IDA in the Operational Evaluation Division. And he'll be talking to us today about lethal debris creation of untracked orbital debris object impacts on small satellites.
Thank you.
I'll give you a 5 minute and 2 minute.
Cool. All right. Lost my voice last week, so I have some water up here. Uh-oh. I touched it and we're back. So can everyone hear me in the back? Great. Awesome. Small room, which is good. Every time I hear Darren's talk, where went, amazing. You guys have a wealth of data. We also have a wealth of data. I think you also have a lot more people working on the analysis. So we're getting there.
Not that many.
Really?
No.
Wow, that's impressive then. Neither do we. Right. So today I'll be kind of building on what Darren showed. He kind of talked about what was up there. Small things, big things. This will be a presentation on what happens if you get hit by one of those things, a small thing or a big thing. I'll define catastrophic throughout the talk, but yeah. I do want to talk about the wealth of data a little bit that we have. We have a bunch of tools here at IDA. This project sort of started as mostly an academic, IDA funded, interested thing. And it has grown to not just what debris is created, but where does it go? What altitudes does it stay in, lifetime and things like that. And a lot of the team is here in the room. So please feel free to jump in if I can't answer something. All right. Briefly talk about the motivation. I think probably everyone understands the motivation for this type of work, but we'll do it anyway. We'll dive into the numerical model of how we simulate debris generation. Go into a couple of results. Darren showed a lot of things, but I'm just going to keep it to maybe 2 findings. That's how I like to do things. And then we'll talk about some conclusions from there. Okay. Yeah. The space environment's crazy. I'm not going to dive into that. There's debris. We have now space as a warfighting domain, the potential for a kinetic anti-satellite impact to happen. Sometimes countries just blow their own stuff up and we don't have to wait for anyone to attack us. They attack themselves and we get to collect data on that and see what that looks like. So thank you to them for doing that. We'll talk a little bit about that later. But for people putting satellites up there, constantly adding more and more things to space, at this point, it's almost a responsibility that you have to let the community know what happens if you were to get hit. We do that for other aspects. It's kind of like maybe an environmental consideration, but the space environment is what we're talking about. If I put a constellation of 1,000 satellites in low Earth orbit, and I know the spatial density of my altitude, I know the likelihood that I might be hit. Let's run a scenario where if I am hit, does it put my mission in danger? Does it put other missions in danger? If I was your neighbor in that altitude, I would want to know that. So at this point, I think it's a responsibility of those satellite owners to do that. This work and much of our division supports the Director of Operational Tests and Evaluation, which provides oversight on operational testing of major acquisition systems. Some of those systems are satellite constellations. Some of those systems are satellites, like GPS is a pretty big one, and many others in low Earth orbit, GEO, all that. So for those, I don't know that any of them are doing this right now, but I would propose moving forward that this be part of their test campaign, this modeling and simulation campaign as part of the acquisition cycle that they're going through. But doing that modeling and simulation, predicting what happens if you get hit is not an easy problem. There are many ways to predict what would happen short of actually hitting yourself on orbit, which of course we would not advise. Typically, we get this information from ground-based testing, which is done in gas gun testing. On the top there, this is a picture from AEDC, Arnold Engineering Development Center or something in Tennessee, where they have a gas gun that can shoot projectiles up to about 7 kilometers per second. Of course, there are limitations to that, but it is a great way to get grounded experimental results. We talked about on-orbit events. Again, it's a great resource for our sensor community to see what we can see. and see what happens if you were to get hit, but it's a very limited data there. Additionally, and what you probably see most of is computational modeling. That's what we're going to be talking about here. Aerospace has a pretty robust modeling department for orbital debris. The national labs do this a lot as well. And we work with them and talk about our findings. And from what I've seen, it's been mostly in agreement, which is great. Great news. Again, limitations with our computational modeling. We only have so much compute power. We're not doing like high-powered computing or anything. It's just on my laptop or on a workstation. Just for context, and this is a picture of our simulation. It takes about 2 to 3 days to run the simulation. It's spatially resolved, time resolved. We have nice pretty videos of all this. They occur over about 20 milliseconds. So a limitation there is we don't really have the computational space or power to go much longer than that. It really adds up quickly. So limitations to all of these, but this is typically how folks are predicting what happens if they get hit. Now, the goals of this study are to use our smooth particle hydrodynamics modeling, and I'll go into what that is, to examine the creation of both trackable and non-trackable debris. From a small hit, think of like a little marble hitting your satellite bus, to a very large, maybe bowling ball or school bus. We don't do school bus size things, but think like that. Were to hit you, what would happen? We did a bit of a parameter study with, of course, big and small objects, but also different shapes, cylinders and spheres, different impact angles, different velocities. It's a lot of data. We haven't even really touched the surface, in my opinion, of diving into it, but that's kind of what our project is working on. And then we ultimately are going to compare those to the industry standard, which widely been used for decades now, a NASA satellite breakup model, which is a pretty simple to apply, but potentially inaccurate in some areas model. And we'll see how our stuff stacks up. So the NASA model that I spoke about is an empirical model based on lab testing that they fit, and specifically applies, as stated in the paper, for catastrophic collisions. Now, what is a catastrophic collision? That is one in which does the laser work? Cool. The kinetic energy of the impactor, 1 FMV squared of the impactor per gram of the target, mass of the target, is greater than 40 joules per gram. So we'll be seeing this 40 joules per gram number pop up. There are 2 relationships from that paper that we'll talk about here. One is the mass to length relationship. So the mass and length of the fragments that are created have some relationship. And here is the fit from their data. It's on a log plot here. The socket test series was a decades ago test that they fit data to, and we'll be plotting our data along this line here. Similarly, the cumulative number of particles created as a function of their mass and length. We'll be seeing this plot frequently as well. So here we have, it's a cumulative sum. You can read it kind of right to left. This is the very heavy objects that are created and very light objects that are created, small masses down here. So you can see it gets up to about 1 million or 10 to the 6th particles are predicted for this type of collision. And we'll be plotting our data along that as well. Now, what did we run? These are the participants in our study. We have two flavors here. We have lethal, non-trackable, which are small 10 gram, 100 gram aluminum spheres at, you can see 15, 45, 75 degrees of incidence when it hits. Various velocities, and you can see that these are all far below this 40 joules per gram threshold. So if we're kind of thinking ahead, this might not align with the NASA prediction because this doesn't meet their criteria for the model. Okay. Conversely, we did a 10,000 gram impactor, both sphere and cylinder, just to add some more runs to our already ever-growing run matrix. In these cases, far surpass the 40 joules per gram threshold. So unless there's new physics happening at a super high energy impacts, then we might expect these cases to align with the NASA model. And just for a visual of what our impactors look like, if this little box down here is kind of the top half of our satellite, the spheres and the cylinders will have the same diameters, 19 centimeters, 30 centimeters, 100, 19, 30, 100. Just had to kind of vary the heights and hollow out the sphere in order to keep the mass the same, but change the diameter. Okay. So for the modeling, we used a smooth particle hydrodynamics code, or hydrodynamics code, or hydro code you might hear in practice. Becky, yeah. For sure.
How do those sizes compare to what you would see?
19 centimeters, 100 centimeters, that kind of order. Well, Darren mentioned, and I wrote this down, that you guys can see down to 2 to 3 centimeters now.
Not yet,
But that's the-
these are trackable fragments.
These are definitely trackable. The idea with these is that they would not be. These are on the order of 2 to 4 centimeters.
Those would be on track.
Yeah. Yep. Good.
That's right, currently non trackable.
Currently non-trackable. CNT. Right, so hydrocode, which Gillen, the astrophysicist, and I think Cameron too, the smooth particle hydrodynamics code used in astrophysics, we also use in hypervelocity impacts. For hypervelocity impacts, at least, it's all happening so fast, such high energy, there's a shock interaction happening. The material itself acts quite like a fluid, which is the hydrodynamics code. And the conservation equations all apply at the particles that you see here. These are the computational kind of like locations where if you think of it, maybe if you think of a typical computational space would be a grid, and all of the equations of motion and things would be calculated at the vertices of that grid. These are all calculated at these free-flowing kind of particle points. Okay, we can talk about more of that later if you want, but that's where I'll stop with that. Now, these particles themselves aren't really physical particles. There is a clustering algorithm that is built within our code here that kind of generates what we're going to consider fragments. And with that, we'll have an XYZ position, velocity, mass, density, length, all that goodness for our fragments that we create. I spoke about the duration of our runs, just more context there. Based on the run that we're doing, range from about 500,000 to 5 million of these simulation particles, and it takes roughly a couple of days. The satellite bus that we're using, our unfortunate target, keeps getting hit over and over and over again, is this 1 meter by 1 meter by 1 meter cube satellite with several internal compartments here, some batteries on the side, a hydrazine tank, which is filled with water in our simulation, so there's no ignition situation. Yep. And if you look on the top here, this little blue ball, this is where we put our impactor, so it's kind of a hit from top to bottom. On the left, we have a 100-gram ball, little tiny guy, 1 kilogram sphere, another 1 kilogram sphere, but the hollowed out one. So that's what those cases look like at time 0. And I should have put a video. We have nice, sexy videos, but I did not. These are snapshots in time of our results. You see, maybe a small little dink here, doesn't really penetrate all the way through, all the way to a huge, massive collision, which would be catastrophic on orbit. Very cool stuff, huh? All right. Great. So the first thing we're going to do is compare it to that, the fragments that we generate to NASA's predicted mass and length relationship from the measurements taken, decades ago. So as a reminder, we'll start with the catastrophic collisions, the big ones. Where's my little thing? 4 kilometers, 7.5 kilometers per second, 15 kilometers per second. Solid black line is that fit, the NASA model, and the black and the pinkish are our results. So first thing you see is kind of close. I had no idea when I plotted for the first time. I didn't know what I was going to see. And it very much fell right on line. I feel confident that those align quite nice. And for comparison on the left with the experimental testing, the gas gun testing, that information is right here. So you see they used a projectile of 150 grams, we use 10,000 grams. Several differences here, but by and large, our results align quite well, which is good news for both our model and for, I guess, using that model. There is a little hiccup here. It's hard to have two screens. I'll give these guys some love. This little tail on the lower end that deviates from the solid black line might be a computational constraint from ourselves, a resolution problem, could be. I did notice that in other experimental testing, who did the same comparison, there was also that little kick up, but I haven't dived very closely into that.
Pete, do you have that comparison with the other curve with the numbers versus mass?
Yeah, that'll be in the second section. Yeah, for sure. Yeah, and just to dive into any one of these, so let's take the 4 kilometer per second example, we have the 3 mass sizes. This is all the same mass, all of the masses on top of each other, and here they are broken up. Okay. So there's just so much to even like go into in these. You can pick, we varied a lot of things. I'll point out that cylinder versus sphere seems to not make much of a difference. Mass of the impactor is really what matters. Again, haven't dived too far into the physics of why that is. I imagine it's just happening all so fast and so quickly, the shape doesn't super matter. And if you note, the cross-sectional area of impact is the same for the cylinder and the sphere. Yeah.
They're all good fits, but it looks like you're getting a better fit for the larger impactors. And now that little kink at the end of the lower side seems to be not as bad for the huge sphere versus the tiny sphere. Do you have any intuition about that?
I don't. I don't. The only thing that I think of is the satellite in this case is almost completely obliterated.
Right, yeah, the whole thing is.
And this kind of just goes straight through like hot butter.
I would have expected the opposite trend if your hypothesis about, just the resolution in your model, you're obliterating everything into SPH, then you're based on the resolution will be based on your clustering algorithm and all of that. But in the case that you're breaking everything up entirely, it looks like your fit is even better. So I don't know what's going on.
Great point.
Yeah.
So Pete, real quick, there's
Sure.
three lesson, master standard breakup model is incomplete. It doesn't include the criteria that was stated in 1992 when the 40 joules per gram was established.
Yeah.
It also says it should be over the speed of sound of the material, which should be 6 to 7 kilometers per second. And the third thing it doesn't include from the initial writing, by the way, I know that because I wrote the paper.
This is why you're here.
Is it also didn't talk about structure.
Okay.
And so structure is very important.
Mhm.
And so 4 kilometers per second, you should not anticipate it to look anywhere near the same, because there would be more strength effects and less of the hydro effects that you would anticipate from being above the speed of sound of the material. And as you get the larger sizes, that effect
Sure
is gonna have a much greater
Yeah,
effect.
yeah.
So that's obvious by that.
Sure.
It's obvious. Come on.
Makes sense.
It's obvious. Thank you.
It's great work, but the NASA Center breakup model did a poor job of documenting the state of the art at the time and saying what the limitations, they overstated the specificity. It's
Yeah.
also not 40 joules per gram, it's 35 to 45. And when I did the paper, I said, we need a lot more testing, don't just use one number, you'll get it wrong.
Okay.
And they're getting it wrong.
It's a shame Joel's not here. He has the same opinion as you.
Okay.
Where is it?
He's in Huntsville somewhere. Whoever said that. Yeah. Okay. How am I on time? Okay, we're all good cooking here. So, now we're gonna go to the small things. Okay, recall this is where it is far below the 40 joules per gram, 35 to 45 joules per gram. And again, kind of fits quite well. The exact physics why the small and the large fit this particular curve very well, not sure. But this is the result there. You still see this little kick up at the lower end, which is why I thought it might have been a computational thing because it was consistent throughout, but it could also be a physical thing that is consistent throughout. So again, this is 10 grams, 100 grams, various speeds. Okay, so now getting to the number of the cumulative sum, the number of particles created, the number of fragments created as a function of mass and length. So this is for the catastrophic collisions with large impactors. This is the 10 kilogram impactor. Just as a reminder, the solid black line is the NASA breakup model, this line right here. Function of mass, so the larger on the far right, the larger masses, not many things are created. You add more and more and more as you get smaller and smaller. So the smallest, you're around 10 to the fifth-ish, is what's predicted. For the catastrophic collisions, our data aligns quite nicely. Very nice. Yeah, and recall that not only are we above the 40 joules per gram, but we're well above that. Okay. And again, the shape doesn't seem to show much of an effect if you compare the black to the pink. And the velocity too. So that's good news. That is good news. And I'm not sure who it's good news for, whether it's good news for NASA's model, whether it's good for our model that it matches that. I don't know who wins here, but it seems like maybe we both do. And everyone who uses these models for their predictions. Because remember, the things that people right now in at the 18th Space Defense Squadron or NSCC or wherever, they're predicting fragment generation. They're running these simulations. And what are they using for their prediction? They might be using the solid black line. So this was sort of motivated by, is that a good idea to use that solid black line? Turns out in some cases it is. Now, maybe this is for a fun discussion, I don't know. But for the small 10 gram, 100 gram impactors, the NASA model, which again, this does not meet their threshold of 40 joules per gram, but far exceeds the amount of fragments that we're predicting. Did you predict that would happen, Dan? Oh.
Yes, so what happens is there's that single term for the slope in the log
Yep.
should be a function of EMR and whether you have the velocity. All it does is it's gonna be a shallower slope.
So that'd be great.
And it actually is a shallower slope if you do that. And it's not that it's wrong, it's that they overspecified it. And that's exactly what should be happening. You get a shallower slope.
Yeah.
They took that term out of the power because they thought it was too complicated. We didn't have enough test cases, but we should maintain it and get more test cases.
Well, that's interesting.
EMR, what EMR stands for?
Energy mass ratio, the 35 to 45 joules per gram,
Mhm.
but and hypervelocity. If you don't meet one of those two, what just happens is you start to get shallower slope.
That's great, because what we were going to do, and maybe what Cameron, we were talking about before, is it seems like it still fits a slope, it still fits
Absolutely.
something.
Yeah.
We were gonna try to play with what that is, what that exponent might be. Yeah.
TD Best's paper on exponential
Mhm.
looks more like an explosion as you reduce the EMR. It looks more like an explosion, it's exponential,
Mhm.
which flattens off there.
I love that, and I'll look into that. We need to find reasons for the things that we're seeing, right?
Absolutely.
Yeah. Okay, I think we talked about all of those things. So to conclude, and we kind of did a nice group discussion already of the conclusions. But for the subcatastrophic collisions, which is below that threshold, aligns well for the mass to length relationship. So we are generating in terms of the geometry of the fragment, what people expect or what NASA expects. But it doesn't align with the number of fragments created. Catastrophic collisions, they both work. Great, good news for everyone involved. Yeah, we found that kind of just on our side, that the shape didn't really impact the results. Mass is really what matters. And Darren, you said that too, mass is king. And this last line just kind of says that we have a lot more things to do, a lot more investigations to make into this wealth of data. So yeah, Courtney, I think I'm on time, hopefully. Love that. Cooking. Any questions? Yeah.
Yeah, when we were talking about the particles earlier, when you were scaling them up to a larger size, right? You started with a dense particle for the small one, and then you having a shell by the time you get a large one. What was the rationale for using that approach, like creating the shell? And does that have any physical impact rather than just say maintaining a constant density of particles, but they're just lighter?
Constant density.
Like the same number of particles, like keeping the same.
In order to keep
particles as you get bigger, just make the particles lighter rather than doing the shell.
Sure, we just wanted to keep the constant mass.
So I'm saying keeping the constant mass, right?
So how would you make the thing bigger?
You make the particles lighter.
The particles lighter, like less dense?
Right, way more particles.
Yeah, okay, so it's the number of particles
issue, and you go low density, the SVH codes get all weird. You don't wanna have unphysical material.
Well, we're making an aluminum sphere, so you can't really change the density of the material. Yeah, we're keeping aluminum, the same thing, yeah.
Here's the other problem. The effective density goes down for these They really crumple up cornflakes. That's what debris is. You need a picture of a piece of debris from a test. They crumple up cornflakes. The question is, how crumpled are they? That's what they're compensating for.
Okay,
Is how much they're crumpled and how much they're ball. And they're all crumpled.
we're all gonna,
Aluminum crumpled cornflakes, right?
got it.
And Brian, just to kind of touch on that
And you
is,
can't launch that in a Savo.
Yeah.
You can try.
right,
You can't launch a cornflake in a Savo.
right, yeah, so we're limited to spheres and cylinders, at least from the experimental side. But Brian, to your point, this one on the right is a hollow sphere, this one solid, goes right through. And there is this one, if you kind of watch the video, it kind of just explodes up because it's just getting pushed up and. So the physics of it all is a little bit different with a hollow sphere versus a solid sphere, but yeah. And yeah, I wish you could launch cornflakes and different.
We tried back in the 90s, it didn't work.
You actually do like laser ablation within foils and fly and get like flyer.
Yeah, but not big enough.
Yeah,
for
not this
kind of-
mass.
Yeah, it's a good idea. We actually did it for smaller stuff,
Yeah.
shielding stuff, they get,
Yeah.
we got NASA a lot with even laser ablation, but that's for looking at millimeter and stuff.
Yeah, the really small stuff, yeah.
Can you get hypervelocity doing that?
Yeah, you get into the tens, so you get faster than gas guns because it's such a, but it's really small.
Mm-hmm.
Yeah.
Right.
And the other argument for sticking with spheres is that's what NASA's always tested, and we have biggest about, not saying argument for, but we have the biggest comparison data set for that, and they have done, I mean, ballistic missile defense, they have done particles and fragments, but it's just a different gun, you can't do it in smaller caliber, these higher hypervelocities, I mean, they do have higher velocities, but they're more ballistic.
Mm-hmm.
But yes, Joel did a paper 20 years ago with shape effects, cubes and things like that. I mean, they have done OJIs and lots of other shapes. Really from years ago.
The biggest issue with this is, and this is where NASA doesn't follow up, is now looking what's in orbit and what's lethality, we don't couple very well, because you're right, it's easy to do that, we have inconsistency, we have inconsistency with what the vulnerability is. So we think a millimeter sized particle is gonna knock us out. If it was, we'd have a lot more satellites failing right now than we do.
That's true.
We actually did a study with the European Space Agency last year, and showed more 1 centimeter than 1 millimeter, because they get so concentrated on these particles, but it's not the same as what's in orbit.
Mm-hmm.
Great for consistency, not good for practicality.
Well, we can make little flakes for our simulations and run that. But no, we can do that. So we should probably do that. That's a good point. Courtney, change it up. Oh, yeah, sure. Sorry.
Yep, from the first talk, it seemed like the probability of collision is usually being tied to kilograms per volume. And then I got from this talk that the size and shape and density matters a whole lot as to the type of effect. So I was curious why, unless I misheard it, why is the probability of collision not tied to like the volume of debris in total as opposed to the mass of debris in total?
Well, in terms of probability, Hannah, do you have a good for spatial density? So is your question about spatial density, like the shell of an orbit at a particular altitude?
If I didn't care at all how significant the impact was going to be, and I just wanted to know the probability of a collision.
That's right.
I think I just care about how much of the space in volume is being occupied by debris.
I think that is accurate.
That's the spatial density term.
Yeah.
That's the spatial density term I showed early on. Number per cubic kilometer.
And then when I said that,
Per cubic kilometer.
I was thinking it was like kilograms per cubic kilometer.
Yeah, no, that was the next, I mean, that was mass, because now is a collision gonna be really big or just kill one satellite? Or is it gonna make 10,000 fragments?
Okay.
So that was the crossover that I was talking fast, that's right.
Gotcha.
yeah. Anything else?
All right.
Cool.
Thank you so much.
Yeah, thanks.